let's start. Uh, Good morning, everyone. We are honored that Professor Inki Kim has joined us for an invited talk on a very important topic and very relevant for our group, which is Metasurfaces for Biosensing, Molecular Diagnostics, and Biomedical Imaging. So, in the beginning, before we give dice to Professor Inki to start his presentation, I would like to introduce him briefly. Professor Inki has been our collaborator for more than 6 to 7 years. We have been working very closely with him during his PhD and now after finishing his PhD. Currently, he's serving as assistant professor at Sungkyunkwan University, SKKU University, South Korea. And he's PI, Principal Investigator of Bio-Nanophotonics Research Laboratory. His research focus is mainly in two dimensions. One is biophotonics and the second one is nanophotonics. On the biophotonics side, he's been focusing on biosensing, bioimaging, diagnostics, and quantum biophysics. While on the nanophotonics side, he has been focusing on metasurfaces for a very long time. And then he has a rich experience towards nanofabrication, electron beam lithography, nanoimprinting, so on and so forth. And also, he's been very instrumental in realizing tunable optics and for the active operation. So, with this introduction, I would like to invite Professor Inki for the talk. So, Professor Inki.
Right. Thank you, Qasim, for the kind invitation. And it's my great pleasure to present my work on biophotonics. So, without much introduction, let me start my presentation. All right. So, yeah, I studied my undergrad and PhD in mechanical engineering at unis and post-tech, and especially during my PhD, my works were focused on nanophotonics, like especially metasurfaces. I utilized it for holograms and multiple lenses, or ultra compact camera, or LiDAR, and so on. So, and also as Qasim introduced, I did many nanofabrication work as well, like electron lithography and nanoimprinting technology. So these are my archive for my PhD study. So hologram and lenses, and here, and also active metasurfaces based on liquid crystal or active semiconductor and so on. And also, I developed several nanofabrication technology, like single-digit nanometer scale fabrication, or 3D lithography, and so on. And also, I was interested in practical application, like a LiDAR or 3D sensor. And after joining SKKU, I switched my research topic to biophotonics. So, the first theme was biosensing. So here I utilized metasurfaces for advanced spectroscopy and also single molecule spectroscopy. So I will tell about later. And also I utilized metasurfaces for bioimaging technology. I developed several new microscopy technology. So let me introduce this theme as well. And also several molecular diagnostic for like a photonic PCR and so on. So our institute also, we are interested in quantum biophysics. So by utilizing quantum metaphotonics, we are developing ultra-sensitive biosensor as well.
So, sorry to interrupt. So can you make it full screen? There are 3 dots near this red telephone symbol. So there are 3 dots. Can you see?
Where?
At the bottom, where you can see mic and then camera, and then you keep moving on the left side. There are 3 dots, vertical 3 dots.
Really?
some of us.
But
Oh, okay. Now it's solved. Thanks. Please.
really? Okay. Yeah. So this biophotonic research, recently I published this perspective article in ACS Photonics. So yeah, here I describe the state-of-the-art research of biophotonics using metasurfaces. So you can take a look at this paper if you're interested in. And yeah, so here we have multiple biosubstance we want to detect, like protein level, or nucleic acid level, or membrane level, and so on. And to detect these substances effectively, we should well design our metasurfaces. Yeah. So by utilizing these device, we wanna tackle these four important area. First one is molecular diagnostics, or this fundamental biophysics research, like cell-to-cell communication. How did these cells they're communicating with each other, and also more pragmatic approach for drug screening. We're gonna use organ-on-a-chip technology, so we're gonna integrate our nanophotonic structure. And also the last one is 3D bioimaging technology for in vitro, especially in vitro imaging. And our institute also, we are interested in quantum life science. So this is not a new field, but people interested in this biophysical study. So this quantum life science, we want to understand biological process on the quantum mechanical perspective. So for instance, this photosynthesis, it's very interesting phenomena. This plant cell, they're absorbing light, and they're gonna produce chemical energy. And during this process, how this light can be converted into chemical energy, to understand that, we need quantum mechanics perspective. So observed light will be transformed into exciton, and this exciton will go to the reaction center, and they're gonna make a chemical energy. And also to understand cell respiration and also magnetic reception, so you should understand a spin chemistry, especially for this magnetic reception. So anyway, there are many interesting examples of quantum life science, and we also want to utilize this concept, especially for engineering application. So let me introduce our first theme, which is metaspectroscopy. So our first question, or our first motivation, was to understand biometabolism inside and outside cells. So especially, this is the first example, photosynthesis. So here, the plant cell, there is a chloroplast where the light will be observed. So here, there is a pigment molecule, which is called chlorophyll. So they're gonna absorb the light, and they're gonna produce exciton, and exciton will move to this reaction center to generate energy. And similarly, in the mitochondria, and this also kind of energy plant. So here, the electron will be moved from one to another, this electron transfer system. So during this transport chain, here the cytochrome C, this is very important enzyme. So our first research direction was to monitor these two important molecules, chlorophyll and cytochrome, to understand metabolism in the plant cell and in the normal cell. So this was our first motivation. And the spectroscopy method we're going to use, this is called PRET, which is plasmonic resonance energy transfer. So I think some of you may heard about the FRET, fluorescence resonance energy transfer. This is the energy transfer between two fluorophore, right? If these two fluorophore are close enough, the fluorescence from the one molecule will be observed directly to this adjacent fluorophore, and then you're gonna see different wavelengths of this emission. So this energy transfer between 2 fluorophore, it takes place within few nanometers, like below 1 or below 2 or something like that. So based on this fluorescence intensity, you can determine the distance between these two molecules, and it can be utilized this concept for molecular imaging. And similarly, here we're gonna use plasmonic scatter. So we're gonna see the interaction between plasmonic scatter and the molecule. This is also interaction between two substances. So let me explain the concept. Here we have plasmonic scatter, then you're gonna have this kind of scattering peak, right? And let's say there is a molecule you want to detect, then it's gonna have it will have this absorption peak. So this absorption peak lies inside of this peak. Then if you mix them together, you're gonna see these kind of quenching dip. So which might be explained by this energy transfer. For instance, the scattering energy from the scattering line from the nanoparticle will be absorbed by this molecule. So as a consequence, you can see this dip, and the location of the dip will be match to this molecular absorption peak. So this kind of late absorption spectroscopy, I think you're gonna familiar with SARA, surface thickness infrared resonance absorption spectroscopy. But here we're gonna measure this PRET in visible frequency or UV frequency, where there are a lot of molecular absorption fingerprints. So anyway, using this PRET, you're gonna detect many different substances. So yeah, once again, this is very simple schematic. If you have a plasmonic nanoparticle and absorbing by a molecule, the molecular absorption fingerprint can be observed by this quantized quenching dip. And later, these energy transfer between nanoparticle and molecule, it was turned out to be electron transfer from nanoparticle to the this cytochrome C absorbing molecule. So the process goes through like this. If you put this nanoparticle inside of the cell, and there is a mitochondria where the electron transfer takes place, and here in the electron transfer chain, you're gonna see this cytochrome C. So the interaction between nanoparticle and cytochrome C will be absorbed by this spectrum. So yeah, there were similar works after these quantum biological electron transfer, which is called QBET as well. So last year, this similar work was published in Nature Nanotechnology, but they utilize this nanoparticle for cancer cell apoptosis. So this is like first cancer treatment using quantum technology. And these scientific news, they cited this QBET work in Nature Communication. And anyway, so this PRET is very straightforward. The thing you need to prepare, you just prepare the slide glass, and then you're gonna spread gold nanoparticle and molecule. And if you detect it under dark field microscope, then you're gonna see this kind of energy transfer, so or PRET. And another advantage of this PRET, as I mentioned, we're gonna detect visible frequency or UV frequency. So you're gonna see you're gonna measure their electronic state, which is different from the infrared. In the IR or mid-infrared MIR region, all of them are vibrational energy. But here, electronic state, we're gonna see interesting dynamics. For instance, the oxidized cytochrome C and reduced cytochrome C, they have different absorption peak. So during the cell respiration or cell apoptosis or necrosis, they have different this oxidized or reduction state. So by monitoring this fluctuation of PRET peaks, you're gonna tell their status. But the most difficult part for this nanoparticle-based prep, you have very small monitoring area because you're gonna trace this single nanoparticle always. And second disadvantage is if you set the nanoparticle, then let's say you're interested in biomolecule, their absorption lie outside of this peak, then you cannot detect, right? So, which means if you select one nanoparticle, then you will have only detect one biomolecule. So to solve this issue, we want to make these metasurfaces. So we can control the alignment and interaction using this nanostructure. So our proposal was to make this chip, and certain part has this blue scattering or green scattering or lead scattering and so on. Then if you spread a different molecule on the chip, then you can detect 3 different molecules at the same chip. So this is our research direction. So to do that, first we designed these metasurfaces. Here we used aluminum, and here we have aluminum back emitter and also this aluminum nanodisc. And also by clustering this nanodisc, so it works as a grating. So yeah, anyway, by changing the geometry of our structure, we can scatter all different visible light. So this is the experimental demonstration. As you can see, by changing the geometry, we can scatter red, green, yellow, blue, and so on. So as a proof of concept, we printed these beautiful color art pieces. So here we have different sized nanodisc. Yeah. Go back to our original proposal. We want to detect 3 different molecules in the chip. So here we prepared chlorophyll B, cytochrome C, and chlorophyll A. And what's interesting to see that they have different absorption peak, especially chlorophyll B. It has absorption peak in blue, cytochrome C in green, and chlorophyll A in red. So if you're using single nanoparticle, you cannot detect these 3 different molecules at the same time. But our metasurface chip, we prepared blue pixel, green pixel, and red pixel, so we can detect these 3 different molecules at the same time. Yeah. So yeah, this is a similar data. We spread all different molecules at the same time, so we can determine, we can detect chlorophyll B, cytochrome C, and chlorophyll A in different pixel location. And so we moved one step further. So here we directly grew the cell on top of the metasurfaces. And also at the same time, here we co-incubated reduced cytochrome C because we want to see released reactive oxygen species, which is ROS from the cell. Then this ROS will transform this reduced cytochrome C into oxidized cytochrome C. So here we prepared 3 different cells: normal cell, tumor cell, and drug-treated tumor cell. And you know, this ROS is very important biosubstance to monitor the status of the cell and also organoid and so on. So, so also this is very important biosubstance for drug screening as well. So especially drug-treated cancer cell, they're releasing the most amount of ROS compared to the normal cell or cancer cell. So to see whether these this new drug is effective or not, you can determine by measuring the amount of ROS. So this is our spectroscopy data. So as prior arts indicated, this drug-treated cancer cell, they are releasing the most amount of ROS, and then cancer cell and normal cell in order. Yeah, so this is label-free ROS detection using the metasurfaces. So still, we are conducting following works for these ROS monitoring using organoid and so on.